Good morning, everyone. We're gonna wait a few minutes. We're still waiting for some more people to connect, so we're gonna wait 2 or 3 more minutes, okay? Indian power sector is facing tremendous environmental challenges in the next few years. Government of India established new standards for the principal air pollutants. This is particulate matter, SO2, and NOx. Although deadlines and limits have been reviewed, they still represent significant challenges for most of the utilities. Good morning, everyone. My name is Enrique Bosch, and I will present an update on the environmental roadmap in the Indian power sector. I will also show you Enerco's vision to meet the new standards. Welcome to this webinar. First of all, from Enerco, we hope you and your families, colleagues are safe in these unprecedented and hard times that we are living everywhere. I also wanted to thank you for taking the time to attend this webinar, and I really appreciate your participation. The duration of the webinar is going to be 45 minutes, and then we'll have 10-15 minutes for questions. You can send the questions anytime during the webinar. Just click on the questions tag the go to webinar platform, and we will reply by the end. If for any reason some of the questions cannot be answered or we just don't have the time, we will take a note and respond later in the week. Also, if you want to contact us, you can do it through this email, infoindia@enerco.com, and the phone number below. I'd like to say a few words about the company, Enerco. We are a group of companies with offices in 9 countries, as you see in this slide. One of these locations is New York State in the US, where I'm today, and here is close to midnight. Enerco has more than 650 people and an average annual revenue of $65 million US. We invest a lot of resources on R&D, and that's why some of the technologies that I'm going to mention today have been developed and patented by Enerco. The company is structured in 3 main activities: engineering, technologies, and consultancy, in order to provide integral services to the industry. Within the technology group, we have a number of different business lines like combustion and environmental technologies. This is where we're going to focus today: SEMS, acoustic solutions, water treatment, and soil remediation. We recently created Enerco India, a joint venture with our partner company Unicom Engineers that provide us with support and resources for this market. Let me introduce Mr. Ram Shankar from Unicom. Ram is also Inerco's representative in India. So Ran, good morning. Would you like to say a few words about Unicon and our collaboration?
Yeah, good morning, Enrique, and good morning, everybody. Hope you're all safe these times. And first of all, welcome you to the webinar. Myself, Ram Shankar from Unicon. We are partners of Inerco in India. Unicon, as such, is an electrostatic precipitator, an ESP company, and we also deal with backhouses, back filters, dense phase conveying systems, and ammonia injection, ammonia flow gas conditioning for the ESPs. So we, Inerco and Unicon, we've been working together for the last, I think, 3 to 4 years now in the Indian market, and we are also working in other markets. So, and we've been working on many projects on NOx abatements, combustion optimizations, and together, I think with our strengths, we are able to execute projects in India. We're already doing so, and I think I'll be the point of contact. And if any queries, I think my phone number and the email IDs are available. You can just call me or just drop an email. We'll be able to respond to you. Over to Enrique to start this webinar.
Okay. Okay, thank you, Ran. Once the introductions are done, I'm gonna turn off the camera for a better signal till the end of the presentation. We're gonna have the question and answers. Okay, so I'm gonna start saying with seeing the table of contents what we're gonna see today. We are going to start with the Indian environmental legislation and current status of compliance. And then I will explain the main low NOx technologies available in the industry. And finally, I will show you some case studies and facilities where we follow a similar approach. So I'm going to start with environmental legislation and current situation. So India's total installed power generation capacity is 373 gigawatts as today. Coal represents the majority of this capacity and also was responsible of almost 80% of the electricity generated in India last year. So it's important to ensure that coal plants are clean and efficient in the years to come. On the 205 gigawatts of coal capacity, approximately 1/3 is central owned, 1/3 is state owned, and slightly more than 1/3 is private sector. So this is what is depicted here. In 2015, the Ministry of Environment and Forests released the new emissions standards for the TPP, the thermal power plants, covering particulate matter, SO2, NOx, and mercury. The limit was based on the GR of commissioning and the boiler size, as you can see in this table. For NOx, initially the limits were 600 milligrams per NOMA cubic meter for units before 2004, and 300 milligrams for units before 2017, and 100 milligrams per NOMA cubic meter for units after 2017. Okay. However, during the last year, there was a lot of discussion about the implementation of these standards, specifically the 300 milligrams limit. And finally, in October this year, it was approved the relaxation of this limit from 300 milligrams to 450 milligrams per NOMA cubic meter. This is what we see here. Also, there is a lot of pressure, especially from utilities, to increase the 100 milligrams to 450, arguing that technologies for 100 milligrams are not suitable for Indian coal. So we will see what's the final decision, but it will not be a surprise to have a number in the middle, something between 100 to 450. Okay. Comparing the implementation of environmental standards with Europe or USA, in these countries, they were applying different phases during a time frame of 10 years approximately. So my guess is that in the long run, these limits will be reviewed again and more strict standards will be implemented. But of course, I'm talking the long term, 10, 15 years, okay? comparing emissions with the US, China, and Europe in these places, in these territories, the NOx limits are in the range between 50 to 200 milligrams per normal cubic meter, depending on the plant. So still, the India standards are quite high compared with these other territories. So in this diluted scenario, we have two groups of technologies, primary measures and secondary measures. Primary measures involve reduction of NOx generation, and these are low NOx burners, certification systems like OFAS, combustion optimizations or combustion optimizers, and I'm going to avoid any non-usual techniques like reburning or fuel gas recirculation because I want to focus primarily on the most extended technologies. Secondary measures are those that are applied after the combustion and once the NOx is already generated. These are SNCR or selective non-catalytic reduction and SCR or selective catalytic reduction. We will talk later about these technologies, but first let's try to characterize the newest scenarios for the coal plants. So in this slide, we are representing coal capacity for central, state, and private plants. Based on the age of the plant, it's possible to establish the new NOx emission limit. As you may see, most of the plants will be affected by the 600 milligrams or 450 milligram limit, and a small percentage will be affected by the 100 milligram, only this part here, or 100 milligrams or whatever the limits is at the end after revision, okay? The majority of the plants will face the 400 milligrams scenario, is this color in light green. And this will be especially in private plants where almost all of them are in this case. For central and state plants, it's also a very significant and important number, those that have to go to the 600 milligrams scenario, these ones here, okay? But as you see, most of the plants will go to 450, and in a second stage or in a second level of importance, they will go to the 600 milligrams scenario. Okay, so what is the baseline of the coal plants right now in India? There is very little information available at this time, but what we are trying to represent here is the average NOx values of those plants that the information is available right now, and those plants that have contacted INERCO. So this is the information we have. It's around 30 units, and I am representing here in this chart. So here we show current NOx emissions versus GR of commissioning. What this chart can say is that all plants will typically require 20–30% reduction. Okay, these are this group of plants here. And then new plants, or after 2007, will require reductions between 25 to 60%, all those here, okay? As you may think, the reduction percentage is quite diverse, and a specific analysis in each plant is totally required. So we're going to find plants with 20% that will find, and we're going to see others with 50% will be required, okay? Okay, so I'm going to talk about now the combustion and low NOx technologies. As I said before, there are primary measures and secondary measures. In first place, we got the combustion modifications, or LMB, low NOx burners, and OFA, overfire air systems. The objective of this technology is the reduction of the O2 content in the first part of the combustion, where the majority of the NOx is generated in the first part. This is what is called combustion in substoichiometric conditions. Also, it tries to reduce the amount of fuel that is combusted at maximum temperature. So here I'm highlighting those concepts. There is a number of different LMB designs, like auto recirculation, split flame, dual nozzle, swirl mechanisms, and so on. All those designs try to get the objectives I mentioned here: stoichiometric combustion, O2 air certification, and low temperature combustion. The definition of these solutions cannot be evaluated locally at burner level because the modification of the burners is going to change the combustion profile and will impact in the boiler performance and operation. So this is an iterative process where several NMB designs are tested and then the results feed a model of the whole boiler. This is what I call here overall boiler impact and assessment here, okay? In all the cases, there is a number of critical aspects that have to be evaluated. First is the velocities in the burner and air nozzles. We normally need to achieve something between 30 to 40 meters per second at the locations to get enough turbulence and good mixing. OFA normally takes 25% of the combustion air. So in line with that, as I said before, the definition of the OFA and SOFA layout is also critical to guarantee that the combustion is complete. At the same time, we have to ensure that the pressure drop at the wind box is enough to achieve these velocities between 30 to 40%. So experience is in definition of these solutions as well as the CFD model capabilities for the combustion processes. Both are critical, okay? I will show you how we have used CFD in one case study later anyways. At Inerco, we have been working for almost 40 years on power plants with different furnace designs, tangential, work-fired, downshot, and different fuels, anthracite, lignites, bituminous, subbituminous, high ash content, high sulfur, natural gas, fuel oil, biomass. So we can provide solutions for almost any boiler design. To evaluate the design, you need to consider a number of parameters. Here are indicated. First one is NOx generation, which is what you look to get with the LMB and the OFA, okay? But also it's important the temperature profile and heat flux. We shouldn't affect heat transmission in the boiler because this would result in less transmission at the furnace area and more in the convective area. That will require more attemperation or even derating the unit. So this is very important factors to be considered. Combustion resident time must be also controlled. We need to guarantee that our solution provides enough time for the particle to be burned. So if we fail in this, that can result in more unburned coal and CO generation. As a consequence, heat rate will be affected, so it will be a less efficient unit. And with the high CO also, there is more possibilities to produce corrosion or severe slagging in certain areas of the boiler. So all these factors must be considered during the design stage. And just to be clear, every boiler is different by design or because the fuel of use, the use of the fuel, or because the way is used. So special attention must be considered in this stage. So when the design is done, we can manufacture the burners, OFA nozzles, and ducts. These are pictures of our burners, okay? Some considerations here are manufacturing procedures, material selection to guarantee durability and performance, assembly consideration, shutdown period, and commissioning. Also, specifically in coal applications, all the mechanisms that these burners have must be reliable and they have to last in a very dusty environment because nobody wants to have a brand new burner with registers that cannot be operated after a few months after the commissioning. So it's very important. At Inerco, we also do burner upgrades. For example, in the picture below, we modify or substitute only the parts that the burners were required. This is something that can be done in some cases when we have more information about the plan or we already have work there. LMB technologies allows reduction in NOx emissions between 30 to 60%, depending on how complicated is the design and the burner retrofit and the furnace modification. Okay, in this slide, we are showing a typical project schedule for an LMB project. It's very important the task name data acquisition. What happens in the first weeks of the project. This is when we collect all the information we require to design the burners and OFA in the engineering stage. Engineering takes around 2 months and 2 months and a half, and manufacturing a little bit more, over 3 months. So implementation of the solution can be done in less than 30 days. This is the installation, and commissioning is typically something around 2 weeks. Obviously, COVID-19 may impact some of these tasks, but it's crucial to be coordinated with the client and suppliers in all the stages of the project. Okay, so there is one interesting concept about combustion modifications that I would like to explain today. In a conventional system, there is a number of situations where the operation requirement impact negatively in the boiler performance. For example, here on the left, we see a boiler that has one of the intermediate mills out of service, maybe because it's in maintenance or just the mill is not available. In these cases, to reach full load, we need to function with all the other mills. So this situation here results in a gap in the combustion area, and is not good from the process point of view. The first thing we are going to see in this is an increment in NOx generation, because there is less stratification of the combustion, and alpha here gets closer to the combustion area. The second thing is that the furnace exit gas temperature, or FEGT, may increase importantly. This is because the combustion has moved up, so more FEGT means more spray at temperature and sometimes derate in the unit. So in this situation, there is less resident time for the particle of coal to be burned, so we can expect more unburned carbon and more LOI. The result of this is a reduction in boiler efficiency, more CO, and we can also expect more corrosion and slagging episodes. Looking at these restrictions in operation, and also the implementation of SOFAs at boilers with no space for new registers, so we found some boilers that they didn't have a space to install SOFAs. So we developed the Flexicon LMP technology here on the right. So Flexicon is a retrofit of the coal distribution system to create a low NOx system by connecting mills and burner elevations. The first modification consists of the connection of all the mills. In this case, even when we have an intermediate mill out of service like this mill is not working. So we're going to have all the burners elevation remaining the same, always. This is always the best picture for the combustion. The second modification is the addition of one of the burners level to the others below. With this, we are concentrating more the combustion at the bottom part of the boiler. The first result is a dramatic reduction in NOx generation. As we see here on the right, this looks more like a SOFA, a separated overfire air between coal and air, which is a stratification. Okay. Secondly, it's a much better control of the FEGT. There is no modification when mills are changed, or even by concentrating the fire at the bottom part, we can have better control. There is more resident time, more time to burn the coal particle, less unburned carbon, and less LOI, which is going to result in better efficiency of the boiler. Okay. One important benefit of the Flexicon is that does not require modification of pressure parts. The connections are done at the coal pipes level out of the boiler. So this simplifies a lot the shutdown periods. This is a technology developed and patented by Enerco, and I will show you how we implement it in a case study later. In this slide, I'm going to talk a little bit about combustion optimization systems and analyzers. This is also a good way to reduce NOx emissions. Historically, there has been neural networks that use a significant amount of data from the plant and provided to the operators with data and recommendations. At Enerco, we developed our own combustion optimizer, which is called Abaco. Abaco uses features from neural networks, but also implement advanced monitoring devices like what I call here Abaco Opticom, which is the flue gas composition analysis in the boiler, or the Abaco LOI for the carbon in ash analysis. So with this information and based on empirical tests that we perform at the plant, we configure an expert system that is able to manage the combustion in closed loop control by acting at the air registers or cold register when it's necessary. Abaco technology is patented by NERCO and is also recognized as BAT, best available technology for NOx reduction and efficiency improvement by the European IPPC directive. And typically the reduction range is something between 15, 20, 25% maximum of NOx reduction, okay? SNCRs, or selective non-catalytic reduction, is a secondary measure for NOx reduction. That means that once the NOx is already generated, we try to reduce it by using this technique. In this case, by the injection of ammonia-based reagent in the furnace. Normally, the reagent is ammonia water 20-25% diluted, or urea up to 50% in concentration. Both reagents are valid, although there is more application in cogeneration with urea, as urea have a better mixing. Better mixing because it takes longer to decompose into ammonia, and also the urea droplet penetrates more into the flue gas stream. Anyways, the injection of the reagent has to be done in a specific range of flue gas temperature, something between 900 to 1150 Celsius, and this is normally above the nose of the boiler. Again, the injection process is critical to ensure the proper mixing of the reagent, and also to provide enough resident time for the reactions. That is why we rely on experience, but also in our CFD capabilities. We have a picture here of the CFD, so we can test different injection strategies with different boiler conditions, like I'm mentioning here, boiler load, XSO2, burners out of service. So we really test all these conditions in the CFD model. But at the end of the day, we implement all these scenarios in a closed loop control system for the SNCR to perform well and properly in all the scenarios. At INERCO, because we are experts in combustion process, we can easily integrate the SNCR in the control operation. Also, because we know a specific characteristic of the combustion and NOx, CO profiles, we can differentiate injection by areas or injectors, maximizing the reactions and reducing ammonia slip. Ammonia slip is the ammonia that does not react in the boiler, because the process is not at the proper temperature or the mixing is not right. Ammonia slip has to be careful control also, because in cold applications can react with SO2 and SO3 and produce ammonia bisulfite, which is very, very sticky and corrosive and affects the air preheaters. This diagram here shows the equipment required by the technology and storage tank, normally for 10-14 days, supply, pumps, and distribution skids. SNCR can provide 20 to 40% reduction depending on the boiler size, mixing capabilities, and design restrictions. Okay, so trying to summarize all the concepts I have explained in this webinar, I've done this table where I'm representing the NOx emission scenario that the power plants are facing. So the limit they have to achieve. The technologies or combination of technologies required to move in that direction is mentioned here. I'm also considering a baseline between 700 to 900 milligrams per normal cubic meter, which is the data that we are seeing in the plants that have contacted with us. And this is a very willful attempt to compare capital cost of the solutions and the reduction rates provided. So for the 600 milligrams per normal cubic meter scenario, we envision units using combustion optimizers and minor furnace modifications. It's a relatively low cost of implementation, but also we see that there will be some units that will require low-NOx burners. The low-NOx burners will become the new standard as the units go to 450 milligrams. All of them are going to require solutions like low-NOx burners. Then we have one more scenario, as I mentioned at the beginning of the presentation. It's not clear. That's why I'm keeping these scenarios of 300 and 100. So I don't know which one will be the limit for the newer plants, but I suspect something in between. For 300 milligrams, again, LMB plus combustion optimizer and furnace modification may be what is needed in some cases. In other cases, it could be required SNCR. And for the most restrictive scenario, for 100 milligrams, it will be required LMB and SCR selective catalytic reduction that I have not mentioned with detail in my presentation because this will be technology requiring the less probable scenario in the short term. SCRs require the construction of a separate reactor with catalyst. The retrofit is a very complex project, and as you see, the relative capital cost is much higher. However, these systems are widely implemented worldwide, and they are one option that I envision more in the long term than in the next few years. Okay. So at Inerco, we can provide all the services and technology that I mentioned. We perform combustion diagnosis, warranty test. We have extensive experience in all kinds of boilers and fuels, and we also have our own capabilities for consultancy and CFD studies. We supply all the technologies commented: low-NOx burners, Flexicon, monitor, SEMS, continuous emission monitoring system. We have our own combustion optimizer, Abaco, and also we have secondary measures like SNCR and SCRs. Okay. So now what I'm going to do the rest of the presentation is to go through case studies. So I'm going to show you 2-3 case studies very briefly, things that we have done in other places. So this, for example, is a power plant in Chile called Bocamina. It's a tangential unit, 127 megawatts with 4 mills and 4 burner elevations. Originally, the baseline was 550 milligrams per normal cubic meter, and the objective was to be below 400. Okay. What we did in this plant was to install new low-NOx burners. This is a picture of what we installed with some schematic views. We also installed a sofa, a separated overfire. You see here in the 4 corners is a picture of what we installed, and these are drawings of the new ducting that we have to install. Okay. This plant also we have to improve cold distribution, installing or modifying the splitters. And we also work on the air preheaters, installing a new double sealing system, a new cleaning system. So the result, it was really good. The NOx emission achieved was below 400, 390, and we were using the OFA only half of the capacity. So it was only using 30% of the air when the OFA is designed up to 25%. So we have more margin to reduce. CO was controlled well below 100 ppm, LOI was not worsened, and heat rate was the same. Okay, this is a good example of application of low-NOx burners in tangential units. In Lada, this is another case study. Lada is a power plant in Spain, the utility is Iberdrola. This is a 350 megawatt plant. Is opposed wall fire boiler, so it has frontal burners in both sides of the boiler. 5 mills with 5 plus 5 burner elevations. In this plant, the baseline was 700 milligrams, and the objective was very ambitious, was to be below 200. That was the emission limit at that time. In addition, this plant had slagging problems, and the top burners were damaged and some corrosion in the side walls. Okay. So this is a view of the previous situation of the plant. This plant could achieve full load with these mills or burner elevation in services. So it was like this, or in this situation, they can go to full load. Okay. The problem with this plant is that they don't have room or space to install new sofa ducts or sofa register. So this was a perfect application for the Flexicon, because we use the existing register, the core registers, as a sofa ports. So with the Flexicon, we were able to concentrate everything in the lower levels, independently which mill is of an operation, and then use the upper registers as sofa. Okay. And the engineering stage, we did a lot of CFD models. We tested different models of burners, looking at geometry, material, and NOx generation. And like I mentioned before, this is a very iterative process. So once we got this, we go to the furnace assessment, and then we try what is the overall NOx generation, what is the heat transfer, how we are impacting to the furnace, velocities, carbon in ash, CO generation, corrosion. In particular, in these pictures here, we were studying how CO concentration was in the sidewalls to mitigate or to avoid problems with corrosion and fouling. So what we install in the plant, then we install the burners. We install the burners here. We also install new ducting connections at the mill level for the Flexicon. We retrofit the wind box for this new configuration where we have everything in the bottom part. And we also install curtain air to protect the sidewalls where we have localized high CO and corrosion. In addition, we install an SNCR with urea. This is a picture of the storage tank, some pumps and distribution system, with the idea of installing, of injecting the urea in the upper part of the boiler. The results of the projects, it was really good again. Remember, we have a baseline of 700 milligrams. Only with combustion modifications, we were able to reach 240 milligrams, which is a 65% reduction, which is a lot. And then using the SNCR, we were able to go below 170 milligrams, which is well below the objective we were required. The third relevant case study, and the last one I want to mention, is Battle River Generating Station. This is a utility, a power plant in Canada at Copower. It's around 400 megawatts. It's a twin furnace boiler design with 8 corners. It has 5 mills and 5 elevations. And the baseline was very, very diverse. It was something between 500 to 800 milligrams. And the idea of the project was to achieve something between 15 to 30% reduction. That was achieved by the end. Actually, the official result was that for all the load range was something between 15 to 40% reduction. Okay. Also, heat rate improvement. We got 0.5% in heat rate improvement also. And the technology we applied in this case was Abaco. Okay, it was only the combustion optimizer. Abaco, as I mentioned before, is an optimizer of the combustion. Is using a monitoring system we install at the boiler. So we get a map here. This is an actual picture of the control room. The information of these monitors is shown here. And then the Abaco is going to work in closed loop control, tuning the air registers and tuning the XSO2 and major parameters of the combustion to be always in the optimum point of combustion, optimum points of performance. Okay. We also are doing remote supervision of the system, so we connect from our offices and we can see in real time what is happening, and we monthly report about the situation to the plant. Okay. And I just mentioned, I'm going to mention just these other cases. We have more references. This is a tangential unit in Los Barrios. Again, the objective was very similar to the one we have in India, to go below 450. We have another plant in Velilla. This plant was using a coal with high ash content, something above 45% ash coal. The baseline was very high and the NOx result was below 500. Again, we use Flexicon LMB and Abaco. And then we also have some other cases like Barranco Granadilla, where we have combined combustion modifications, but also SNCR to be below 200, or with the SNCR to be below 150, which is a great result. And last but not least is one very important project for us. We are doing now Bandel it's our first project in India. It's a 215 megawatt plant, wildfire boiler. The objective in this project is to be below 500 milligrams, and the project is being executed at the moment. So we are manufacturing the burners and should be complete anytime soon. And the technologies that we are applying is low NOx burners plus OFA. Okay. So that's the whole content of the presentation. So now I have to thank you for your attention, and I'm gonna go to the to see if we have any questions in the chat. As I mentioned at the beginning, you can write your questions, and we will try to reply everything here now. So questions are welcome now. Okay, so let me check, because we have some. Okay, let me open this. Okay, let me reply some questions. Okay, I got a question here. Is what is the NOx emission perspectives beyond the new standards? Okay, well, this is a really good question. Well, my opinion is that the new environmental standards have been quite relaxed. So 600 milligrams, it's okay for all units. 450 for new units is quite high. I expect in the long term to have a new adjustment, because if we compare with standards in other countries like China or US or Europe, we're going to see very frequently 100, 150 milligrams. Those are the standards for all and new, so for all the plants. We'll see what happens with the 100 milligrams limit. So we don't know yet, but I'm expecting also something in between. I don't expect 100 milligrams. I would expect something between 100 to 450, but we'll see along next year what's the final decision. Okay. Okay, so I have one question here. How COVID-19 may impact in the execution of these projects? Okay, so this is a good question. Actually, it's a real question. Ram, I think because you are the person dealing day to day with this, maybe it would be it would be good if you can reply something and say how we are doing now.
Yeah. See, we got this contract of Bandel during the lockdown, when the lockdown was at the peak of the time, and I think what we did was we had some interferences in the project because of the COVID-19 due to the travel restrictions, especially in data collection. When we had to go to the site and visit and collect some measurements, collect the data, collect samples, see for interferences for OFA, see the orientations of the burners. I think these things were a little disturbed, but the supply chain as a whole was not fully disturbed, because our supply chain is of Energo and Unicon is mostly, I think 80% is concentrated within a same state, and the rest 20% comes from outside, but those are all accessories that goes in, like the flame scanners and the electrical accessories and the control systems. So I think COVID-19 did not affect us much, but I think there was some issues in data collection. I think not much. Still, I think we're still
Hello, Ram. I don't think we can hear you now, Ram. Okay, Ram. We're having some difficulties with the connection with Ram. Okay. So yeah, we have some difficulties with RAM. Anyways, summarizing, this is something real which is happening in the project with Bandel. Especially important is the first part of the project. When we do the collection, there were some travel restrictions that, with the collaboration of the client, we were able to solve, and also with local resources that we were using. Right now, the project is doing well according to a similar project schedule that I presented to you. So hopefully by the beginning of next year, the project will be completed. Okay. I think we still have time for one or two questions. I know. Okay, I have a good question here about LADA. In the LADA case study, you said that you concentrated all the coal into the lower elevations and use the upper layer of burners as sofa. That's correct. Effectively, you lost use of some burners. Okay, that's correct. Did it impact the MCR capacity? No, because what we are doing in a project like LADA is that we are using the existing burners, modified, of course, and those burners have more capacity. Okay. Of course, we need to analyze that the burner with a little bit more capacity is possible in that boiler. That's important. But in the case of LADA, as very common situation, they were using a different fuel, different coal from the design. So in that case, we could modify and do that modification. Okay. And we are almost on time. What I'm gonna do, I think I have one more question here. What I'm gonna do is the rest of the questions we will reply later during the week. So I will contact you, or we will contact you later in the week. Okay. Ammonia slip. What is the ammonia slip limit for the SNCR? Well, this is an important question. Ammonia slip is the ammonia that has not reacted in the SNCR injection, in the urea or ammonia injection. It's a very important factor because ammonia is going to react. The ammonia that has not reacted in the combustion area is going to react with SO2 and SO3 at the air preheaters, and then it's going to produce ammonium bisulfate, which is very sticky and corrosive. So you have to control that parameter. And the standard right now is that for high sulfur boilers, you can go with an ammonia slip low as 5 ppm, 4 ppm with SNCR. For SCRs, normally the standard is well below, it's 2%, but 5 ppm will be a good number. With coals with lower sulfur composition, you can go up to 10%. That shouldn't be a problem. So those are the standards at the moment. Okay. Okay, so yeah, I think we are on time. I have to say thank you again, everyone, for attending this webinar. I hope you have enjoyed the presentation. I will share the presentation and also probably the video with all of you in the next days. I have a couple of other questions probably here. I'll try to replay later on the week. And like I said, if you have any inquiry or if you have any questions about what we have discussed today, you have our email here, infoindia@inerco.com, and you can contact Ram, which is our local person there for all these projects and opportunities. Okay. So one more time, thank you very much for attending, and stay safe and have a great day over there. Thank you. Goodbye.